Hello, my name is Andrew Bernhardt with the student ID 20065178890, and I will be discussing the dual axis solar tracking system with LDR sensors by using the Wheatstone bridge circuit. So this presentation will cover the problem versus the solution. Next is this electronic design, followed by the Wheatstone bridge circuit, and last but not least is the output power result. So the main problem is in pursuit of maximizing the output power of PV panels during the day, they must be kept at a perpendicular angle towards the solar radiation. So the solution that we can come up with is the dual axis solar tracking system, which offers a much more accurate ability in following the solar radiation path by adjusting the PV panel in two axes, namely X and Y axis. So we will be using the sensor-based solar tracker system, which is a closed-loop control based on the active tracking system, referring to the feedback circuit that implements LDRs. And the light-dependent resistors itself will track the sun independent of its geographical location. And since we will be using the Wheatstone bridge circuit, it is actually crucial in achieving higher sensitivity, measurement, and ability to compare between values of LDR in the control circuit. So from implementing such a system, we'll be having an efficient system, a simple system, and a low-cost system. So in the electronic design of the DAST system, it will operate in both manual and automatic using three status keys, namely the high, middle, and low. In the high key, it will automatically operate with the help of control IC circuits, transistors, and LDR sensors. In the middle key, each button can move the system in one of four cardinal directions, as well as calibrate the tracker system. And last but not least, in the low key, the system will not operate. So as for the Wheatstone bridge circuit, it will initially measure the variations of sensors' resistances. And as we can see on the left side, the image of the half bridge structure, it will be measuring two elements with the same type to acquire higher sensitivity. So it will provide a signal in the output of the resistance sensors, including the LDR sensors. And by having this Wheatstone bridge circuit, the DAST system will be more sensitive and respond faster. So as for the Wheatstone bridge circuit formulas, as for the first formula, the resistance Rx of a linear resistance sensor is described as the first equation, where K is the conversion constant of the sensor and X depends on the measured quantity, while Rho is the nominal resistance of the sensor element. In other parts of the bridge that has a resistance equal to R0, then the output voltage of the bridge will be equal to the second formula or the second equation, where E is the bridge power supply voltage and Kb is a bridge constant. The result of the output bridge voltage will be of a nonlinear function, and since the percentage of change in the resistance element is very low, therefore the nonlinearity will also be low. And as for the last image right here, we can see this is the output power results by using the solar tracker and the fixed panel. And we can see that from using the solar tracker, it allows the PV panel to follow the solar radiation, allowing maximum output power of the PV panel throughout the day. Whereas using just a uniaxial fixed panel, it can only follow the sun for one time, which is the highest time of the day that the sun can provide its solar radiation, and it can no longer follow the sun after that. And I believe that it's the only time that the sun or the solar radiation will be perpendicular to the PV panel by using the fixed panel. And so I believe that's everything that I have to present for this paper, for this journal. Thank you for your attention. I hope this gives you further insight as to the improvisation or further research of PV panels.